Auzu billahi minash shaitanir rajim. Bismillahir rahmanir rahim. Dear student, Assalamu alaikum. My name is Dr. Muslim Khan, Assistant Professor, Department of Chemistry, KUST. Today, in the course CHEM451 Molecular Spectroscopy, the topic of our discussion is the second part of nuclear magnetic resonance spectroscopy. As we were discussing the location of the signals, we discussed the chemical shift that more electronegative atoms de-shield more hydrogen and give larger shift to the signal in a spectrum. And effect decreases with distance. Additional electronegative atom cause increase in a more chemical shift. For example, this is the example of chloromethane and dichloromethane and trichloromethane. Here you can see when one electronegative element is attached, so it de-shields these three protons and it shifts the chemical shift. The spectra, the peak of these hydrogen atom will appear at 3.05 ppm. When one more electronegative dichloromethane, when one more chlorine is attached, so it more de-shield these protons, and the chemical shift is more shifted towards a downfield, that is 5.30 ppm. While when a third chlorine is attached to the same carbon atom, so it more de-shield this proton, so the peak is more shifted towards a downfield, that is 7.27 ppm. So this shows the effect of electronegative atoms over the peak in a NMR spectrum. Here are some of the example of typical, here are some of the typical values for different groups that where it will appear in a mass spectrum. For example, alkane will appear, the peak for this hydrogen, which is in alkane for methyl group, is at around 0.9 ppm, while the CH2 group in the same alkane, but it is attached to carbon atom on this side, carbon atom on this side, so it will appear at 1.3 ppm, while the same alkane, this is when tertiary carbon atom, hydrogen attached to the tertiary carbon atom, then there will be more shift towards a downfield, that is 1.4 ppm. While hydrogen attached to this carbon atom, when itself it is attached either to this is to ketonic group, and then it is shifted to 2.1 ppm, while hydrogen attached to acetylenic carbon 2.5, while hydrogen attached to the carbon atom, when on one side it is attached to the alkyl group, on the other side it is attached to the halogen atom, it is more shifted towards a downfield 3 to 4 ppm. Similarly, hydrogen attached to the carbon of a double bond, that is around 5 to 6 ppm, while hydrogen of aldehyde around 9 to 10 ppm, carboxylic acid 10 to 12 ppm, and etc. So you can see these values here in this table. So this is the example of aromatic proton aromatic circulation of electron ring current, and this aromatic protons induced a field that reinforce the external field, so more deshielding occur. That's why the peak will appear more towards a downfield around 7 in between 7 to 8 ppm. So similarly, the vinyl proton also induced the field, reinforced the external field, so more deshielding. Although deshielding is less in compare to aromatic protons, so the signal will appear in between 5 to 6 ppm. While acetylenic protons, the signal will appear, the shielding is less and deshielding is less in comparison to aromatic and the signal will appear around 2.5 ppm. Aldehydic protons induce the field which also reinforce the external field, so more deshielding occur, even more deshielding than aromatic protons. So the signal will appear at in between 9 and 10 ppm. While you can see that OH and NH signals, so chemical shift depends on concentration. Hydrogen bonding in a concentrated solution deshield the proton, so signal is around 3.5 ppm for NH and 4.5 for this proton, which is connected to oxygen atom. Because oxygen is more electronegative than nitrogen and it deshield the proton more, so the signal will appear more towards a downfield 4.5 ppm. So proton exchange between the molecule actually broadens the peak. So here is the example of carboxylic acid. So in carboxylic acid, there are two types of proton you can see in this spectra. One proton is connected CH3, and which hydrogen proton is connected to carbon atom, and this is a carboxyl group. So one proton is of this carboxylic acid proton. So this carbon atom signal will appear, although you know that signal for proton in alkane is appear around 0.9 ppm, but this carbon atom, the environment of this carbon atom is different because this is attached to the carboxyl group. So it shift even the signal for this hydrogen to 2 ppm. This is for TMS per standard, but for this one this is a carboxyl group in between 9 to 10 ppm, because this is a proton of carboxylic acid, because this is directly attached to another oxygen atom which is more electronegative, so it reinforced the external field, so more shifted towards a downfield. So equivalent hydrogen have the same chemical shift. So this is, you can see these are the number of hydrogen to attach to carbon atom on the one edge of a molecule directly attached to the oxygen atom. So this is a signal for TMS, and this is for a hydrogen atom. This is directly attached to oxygen atom. It will be more shift towards downfield. So that's why signal appear at around 3.9 ppm. While this is B, on the one hand, it is attached to carbon atom, which itself is attached to two oxygen atom, and on the other hand, this carbon is attached. This is attached to carbon atom is attached itself to oxygen and another metallic group. So the environment of this hydrogen is different than this one. and the environment of this hydrogen is even different than this one, because this carbon atom is having hydrogen atom, but on the other hand this carbon is not having any carbon atom on this side. Also this carbon atom is attached to carbon atom, not directly like this carbon atom to oxygen atom. So the environment of these three types of protons, this one is different. That's why it is denoted by A, B, C. But this is more shifted towards a downfield. So this signal is for A, and this is different than this. So this is B, and the last one, this one is C. So this is the chemical shift of a different types of protons, depends on the environment of a protons. So the area under each peak, or the height of the peak, is proportional to the number of protons. So whenever you are doing integration, so either it is the area under each peak, either it is the height, the intensity, which shows the number of proton. Because here, these are 3 protons, while these are 9 protons. So the intensity of these proton will be less in comparison to these 9 proton. This will be less, and this will be more shifted towards a downfield. Like you can see, that is around 3.2 or 3 ppm, while that is 1.2 ppm, because these protons are attached to the carbon atom, which itself is attached to a tertiary carbon atom. Shown by integral trace. So how many hydrogen? When the molecular formula is known, each integral rise can be assigned to a particular number of hydrogen atom. So here in this molecule, you can see there are 4 types of proton. One is this A, and this A. These two types of proton have a similar environment attached to the carbon atom, uh, uh, which itself is attached to another carbon atom and oxygen. So for these proton, the environment is the same. That's why it is assigned A, while this proton is directly attached to the oxygen atom. So this is the environment of this is different. That's why it is denoted by D. While this is different, this is B and this is C. So here in a spectra you can see number one. So this is A, these A. So there are 6 proton. So you can see even the intensity of these proton. This is for TMS 0 ppm signal. While for B, these are 3 proton. There are 3 proton, but there is more shifted towards a downfield around 2.1 ppm. While then this is attached to another 2 carbon atom, but one carbon atom is attached to oxygen atom, another one is to methyl and oxygen atom. So this is C, these are 2 protons, while D, this is another one which is attached to directly oxygen atom, more shifted towards a downfield. So this is how you are interpreting NMR spectra. Yeah. Another point we want to explain, spin splitting. So sometime you can see an NMR spectra, this peak will be split either in 2, 3, or even 4, or even 5. Basically non-equivalent proton and adjacent carbon atoms have magnetic field that may align with or oppose the external field. So there are different kinds of possibilities that may align with or may oppose the external field. So this magnetic coupling, when either it align with or oppose, this magnetic coupling causes the proton to absorb slightly downfield, and when the external field is reinforced, and slightly upfield, so when the external field is opposed. So that's why all possibility existing. So signal is splitting. Once again, I want to repeat. So in NMR spectra, the signal is sometimes splitted. Basically, non-equivalent protons and adjacent carbon have magnetic field that may align with or oppose the external field. So this magnetic coupling causes the proton to absorb slightly downfield when the external field is reinforced and slightly upfield when the external field is opposed. So all possibility exists. So signal is splitted. Like here, this is the example. These are non-equivalent proton and adjacent carbon atom. These two carbon are adjacent carbon atom. Here with this carbon atom, there is only one hydrogen atom, and on this carbon atom, there are two hydrogens. So this is denoted by Hb and this is denoted by Ha. So here for this for these carbon atom, so there are two protons but the signal is split. So in one case it with this one, so it is either opposes or reinforce the external magnetic field. So this is splitted into two, one downfield and one upfield. So, but this one, it is splitted into three. So in coming slide, you will see how it will split the n+1 rule, the splitting. So you will see that how it split into three. So it means that here this signal is splitted into three or two or even four sometime. So this is because what we have explained in splitting. So this is this is for these. So H reinforce the field. It opposes the field. So because the adjacent carbon, there is only one hydrogen atom. So one hydrogen atom, there are two possibilities. The one possibility that it reinforce with external field. With this field, it reinforce. So because it reinforce, so this is the signal for reinforcement. So it more shift. So a chemical shift of because of this HA, and here it oppose. When it is opposed, so it is more upfield. So that's why the signal for these two hydrogen, will be splitted into a doublet adjacent proton. While signal for this hydrogen is split into three. How? Like because of these hydrogen atom, there are two. So in one case, one possibility that both Hb proton reinforce the field. When it reinforces the field, it will give a signal for this hydrogen like this. The other case is it opposes the field. So this is the possibility. While the third case, either the one is opposing and another one is reinforcing, or this one is reinforcing or this one. So it means the third possibility. That's why it is splitted into a triplet. This is n+1 rule. If the signal is split by n equivalent proton, it is splitted into n+1 peak. For example, a number of equivalent proton causes splitting is 0, so the signal will be 1. But if the number of equivalent proton, like in the first case, we saw n+1, it means 1 plus 1 is equal to doublet 2. If the number of protons are 2, like in the third case, in the second case, so 1 plus 2 is equal to 3, triplet 1, 2, and 1. So similarly, quartate, quintate, sextate, and septate. So range of magnetic coupling, equivalent proton do not split each other. Proton bonded to the same carbon atom will split each other only if they are non-equivalent. Proton and adjacent carbon normally will couple, and proton separated by 4 or more bond will not couple. So splitting for ethyl group. For example, ethyl group attached to the benzene ring. First of all, here there are three types of hydrogen. One hydrogen is of these hydrogen directly attached to aromatic ring, and the other one in ethyl there are two types. One for this and attached to this carbon atom, and these three attached to this carbon atom. So first of all, so this is a signal for this hydrogen, this, and this is a signal for this hydrogen. While you know that for aromatic ring, it will be n between 7 to 8 ppm, what we have saw in the table, because that will reinforce, it will more, there will be more shift of these hydrogen while attached to the aromatic ring. So splitting for isopropyl group, you can see the isopropyl group. Isopropyl group, so this is A, the signal for A, and this signal for B, uh, this signal for B, while this signal for C. And splitting, you can see according to what we have saw in the that n+1 rules. Chemical shift will depend on the concentration and solvent. To verify that a particular peak is due to the OH or NH, shake the sample with D2O, deuterium oxide. Deuterium will exchange with OH or NH proton. On a second NMR spectrum, the peak will be absent or much less intense. So last, coming to the application of NMR, nuclear magnetic resonance spectroscopy is a non-destructive analytical technique that is used to probe the nature and characteristic of a molecular structure. A simple NMR experiment produces information in the form of a spectrum which is able to produce detail about the type of atom present in the sample, the relative amount of atom present in the sample, the specific environment of atoms within a molecule, and the purity and composition of the sample, and structural information about a molecule, including constitutional and conformational isomerizations. So for this topic, you can see Gary Christian or Douglas or Wells, atomic absorption spectroscopy, principle of instrumental analysis and instrumental analysis. Thank you very much.